now we will discuss about the properties of resins. So first we will discuss the physical properties of resins. Now resins they occur as hard, transparent or translucent, brittle amorphous material. So as I mentioned in my first slide that these are the uncut jewels that was mentioned by Robert Frost in his poem The Gum Gatherer. So they basically occur as hard, transparent or translucent, bitter amorphous materials which are generally heavier than water, and they have a specific gravity in the range of 0.9 to 1.25. So we also discuss their fusibility in one of the definitions, that is these resins are fusible and on heating they first get softened and ultimately they melt without undergoing any sort of decomposition or volatilization. This is another important character of resins which differentiate resins from the gums. Now whenever these resins are heated in the presence of oxygen or in the presence of air, they burn with a smoky flame because of presence of large amount of carbon atoms in their chemical structure or in their composition. And whenever these are heated in absence of oxygen or in an enclosed chamber, then they undergo decomposition. This is their major character, I will say, regarding their physical appearance or physical character of resins. And these resins are bad conductors of electricity, and sometimes certain types of resins are also used in insulating materials in electrical appliances. They are practically insoluble in water, but they are soluble in alcohols, mainly ethanol or methanol. They are also soluble in volatile oils, fixed oils, chloral hydrate and non-polar organic solvents like benzene or hexane, petroleum ether or diethyl ether or toluene, and so on and so forth. Now we move on to the chemical properties of resins. Now as we discussed that these resins are largely composed of volatile or non-volatile terpenoidal compound and phenolic compounds. So in the nutshell we can also say that the resins are the secondary metabolites which lack nitrogen atom in their structure, and as we discussed that on burning they burn with the smoke in the presence of air. This also shows that they are carbon rich entities and they also have few oxygen atoms. Now whenever the resin is secreted from the plant, and if you allow that resin to stay on the tree, or if you collected that resin and did not store that resin properly, then those resins are liable to undergo atmospheric oxidation. It means their constituent, they react with the atmospheric oxygen and start producing artifacts, and these artifacts basically cause the darkening of the color of the resin. So if you are collecting a resin directly from the plant and that resin is light creamish or buff colored, then if you are not storing that resin properly in an oxygen free atmosphere or in an airtight container, then that resin will undergo oxidation, and slowly the color of that resin will change to brownish or dark reddish brown in color. Now as we discussed in the definition, that resins are nothing but they are complex chemical entities, and they are a mixture of numerous compounds rather than a pure chemical entity. Now these are composed of three major components. If we want to categorize those components into categories, then three major categories are there. One is resin alcohols, resin acids, and third one is resins. And we are going to discuss the detail of these three classes in the subsequent slides. Now terpenoids, as mentioned in the definition, these are the major constituents of the resin, and if the resin is having large proportions of essential or the volatile oil in its composition, then mono and sesquiterpenoids are the major components, whereas if the resin is the normal resin, that is it is having very less volatile oil in its composition, then diterpenoidal components are their major constituents. Now whenever the resins which are rich in acid, which we also call them as acidic resins, whenever they are treated with alkalis, they basically produce soap like compounds or soap like structures, or we can say soaps, which are also known as resin soaps, and these soaps are of inferior quality and they are used largely for the industrial purpose where they don't require I will say good quality soaps for washing purposes. Now we move on to the details of the composition of the resin. As we discussed that there are three major components: resin alcohols, resin acids and resins. Now resin alcohols are nothing but these are the complex high molecular weight alcohols, and depending upon their chemical nature they can be further classified into two categories. First one is resinotenols and the second category is resinols. Now as the name indicate, resinotenols, these are the alcohols that give tannin like reaction whenever they are reacted with iron reagent, specifically ferric chloride. So as we discussed in my previous lecture that the tannins on reaction with ferric chloride, they either give blue black color or the blue green color. Similarly, resinotenols are the type of alcohols which on reacting with ferric chloride or any iron reagent, they give tannin like reaction or tannin like results, and whenever they are reacted they form phenoxides and get solubilized when they are mixed with aqueous alkalis. So resinotenol rich resins, they are soluble in the aqueous alkalis, and the common examples of resinotenols are Cea resinotenol, which is found in Sumatra benzyne, and Tolu resinotenol, which is found in balsam of Tolu. And the second type of resin alcohol is resinols, which do not give any specific type of specific tannin like reaction as we see in case of resinotenols. First difference, and second difference is that these resinol rich resins are insoluble in aqueous alkalis, and the common example is benzoresinol from benzoin and storesinol from storex. And the second category of constituents that are found in resins is the resin acids, and these are nothing but the mixture of carboxylic or phenolic acids which can occur in both free form and also in the form of esters. And whenever these resin acids they are mixed with alkalis, they give rise to inferior quality soap, as we discussed in during their properties. And the most common resin acids found are abiatic acid or pymeric acid. Apart from that, various other resin acids like comephoric acid, which those are also found in different types of resins. Now whenever these resin acids are reacted with metals, they tend to form their metallic salts, and these metallic salts are known as resinates. And as we discussed that these resin acids are soluble in acids, resinates are also they are soluble in alkalis, and on reaction with alkalis they form soaps, and they are widely used in the manufacturing of varnishes. The third category is of resins. Now resins are the chemically inert substances or chemically neutral substances which neither react with acids nor react with alkalis, and the most common example of the resin is the Draco resin, which is also known as blood dragon resin, which is obtained from Demerops draco. You can see the picture of the plant on the slide also. Now apart from their reaction or their inertness towards the reaction with acid or alkali, these resins are also inert or stable towards any kind of climatic or weather conditions. They are quite stable towards the oxidation that is caused by the oxygen present in the air, or they are quite stable towards the hydrolysis caused by the moisture that is present in the air or during the rainy season. And since they are stable towards this climatic oxidation or hydrolysis, these are largely used in the manufacturing of varnishes as well as paints that protect the wooden boards or the wood from the natural oxidation or the harmful effects of the moisture on the wood. Now we move on to the classification of resins. Now resins can be broadly classified either on the basis of their formation or on the basis of their composition or the combination in which they occur in the nature. Now on the basis of the formation, resins can be classified into natural resins and the prepared resins. Now, natural resins can further be categorized into physiological or primary resins and non-physiological or pathological or secondary or induced resins. Now, physiological resins or the primary resins are the resins that are produced naturally inside the plant as a normal process of their metabolism. Since resins are secondary metabolites, so such kind of physiological or primary resins, they are formed by the normal metabolic processes or physiological processes that are going inside the plant. So you don't have to give any I will say artificial conditions to produce those resins inside the plant naturally produces it. Whereas the non-physiological or pathological, which are also known as secondary or induced resins, these are the resins that are not produced as a part of normal metabolic processes, but these are produced only whenever any kind of injury or infection is inflicted onto that particular plant. So as we discussed that whenever you give an injury to a resin producing plant, or you inflict any kind of bacterial infection, fungal infection, or you treat that particular area of the resin producing plant with fire or acid, so this kind of trauma induces the defense mechanism inside that particular plant, and by virtue of that defensive mechanism, that plant start producing resin inside it. And such resins which are produced only after the infliction of any kind of injury or infection, they are known as non-physiological. So non-physiological resins, or since they are produced only after injury or any kind of infection, they are also known as pathological logical resins, and vis-a-vis induced resins. So you are inducing, you are providing certain induction conditions which leads to the production of the resin inside the plant, and the most common example for that is benzoin. So this was all about the natural resins. Now we move on to the prepared resins. Now these are the resins which do not secreted by the plant as such, but these are prepared after only specific extraction procedures, such as you extract the plant material with alcohol, and since the resins are insoluble in alcohol, we concentrate that aqueous extract and put that concentrated alcoholic extract into water, and since resins are insoluble in water, they get precipitated down, and the resins of podophyllum and jalap can be produced or can be extracted by this method. Similarly, other methods of getting prepared resin is you can extract the plant material with lower boiling point solvents, and then you can distill off that solvent to remove the volatile impurities, leaving behind the resin, as we normally see in case of oleogum resins, which we are going to discuss in the next few slides. Then you can also extract the plant material with 95% alcohol to remove the gummy material, or you can by extracting with 95% alcohol, you can remove the resin, and the gum, which is more or less water soluble, it remains behind, giving you a purified form of the resin. So these are few methods by which you can get an idea that what is the difference between a prepared resin or a natural resin, which can be physiological or pathological. Now we move on to the classification of resins on the basis of their combinations. The combinations in which these resins occur in nature. First one is acid resins, and such resins are mainly composed of carboxylic or phenolic acids, such as colophony or myrrh. Colophony is rich in abiatic acid, and myrrh is rich in commiphoric acid. So as you can see in the picture, the golden brown color of resin exuded from the colophony tree. So acid resins which are rich in the phenolic or the carboxylic acids. Then we have ester resins. Now in these resins, these carboxylic or phenolic acids, they largely occur in the form of esters. So whatever, if the resin is having large amount of esters in it, and these esters will be of those carboxylic and phenolic acids, then we call them as ester resins. And the most common example of ester resin is benzoin, which is rich in benzyl benzoate, and storax, which is rich in cinnamyl cinnamate. Now benzyl benzoate is an ester of benzoic acid, whereas cinnamyl cinnamate, which is found in storax, is an ester of cinnamic acid. Next we have is the oleoresins. Now oleoresins, as their name indicate, oleo means oil. So whenever the resin occur in combination with oil, or we can say that whenever the volatile oils form or the fixed oil forms the major portion of the resin, then such resins are known as oleoresins. And as we discussed that whenever the volatile oil is the major component of the resins, then mono and sesquiterpenoids are the major components of that particular resins. So such kind of oleoresins where mono and sesquiterpenoids are the major components, they are largely found in the angiosperm type of plant, resin producing plants. Whereas in case of gymnosperms, normally the resins that are rich in diterpenoids, which are non-volatile in nature, then such resins are found in more in gymnosperms. But as such, there is no hard and fast rule for the distribution of this type of resin, but on an average, or I will say in general, the mono and sesquiterpenoid rich oleoresins, they are found in angiosperms, whereas the resins that are rich in non-volatile terpenoids, specifically diterpenoids, they are found in the gymnospermic resin producing plant. And most common example of oleoresin in our case is the turpentine resin, and the second one is that of the ginger. Next we have is the oleogum resin. So as the name indicate, this resin occurs in combination along with volatile oil as well as along with the gum. So gum are carbohydrate in nature, oils are terpenoidal in nature, and when these two type of secondary metabolites, they come together in a resin form, then we call it as an oleogum resin. And the most common example of oleogum resin is Asafoetida, which we commonly known as hing. So whenever you, as you can see in the picture, on the left side is the plant of Asafoetida, and normally the Asafoetida plant is cut near the base or near the crown of the root, and whenever the stem is cut near the crown of the root, then the creamish white resin oozes out from the crown region of the roots and rhizomes of Asafoetida, and those resin, which we call it as hing, is further treated and purified before it is being marketed. Another category is of gum resins, and these resins have large proportions of gums in their composition, and that is why the name gum resin is given to them. And the most common example is ammoniacum gum, which is obtained from ammoniacum or Dorema ammoniacum, and this ammoniacum is largely used as a substitute or allied drug for the true Asafoetida, which is obtained from Phoetida ferula. Another category of resins is the glycoresins. So as again the name indicates, glyco means glycoside, and whatever glycosides are nothing but these are the secondary metabolites which occur in combination with sugars. So when the resins occur in combination with sugars, they are known as glycoresins. And the common example is podophyllose resin, which is obtained from the roots and rhizomes of podophyllum. And as we discussed, this podophyllose resin is a prepared resin wherein the powder of the roots and rhizome is first extracted with alcohol. That alcoholic extract is then concentrated under vacuum or under reduced pressure. This concentrated extract is then poured into water, which causes the precipitation of the resin, and from there those precipitation or the sticky mass which settles down, it is separated, and that is considered as the podophyllose resin. And the last category in the classification is that of the balsams. Now these are nothing but these are the resinous mixtures which have high proportions of aromatic or phenolic acids. Aromatic balsamic, you can also call them as aromatic balsamic acids, or you can call them as phenolic acids. So acid resins were rich in carbohydrate or phenolic acids, but balsams are specifically rich in phenolic or the balsamic acids like benzoic acid or cinnamic acids. Now balsams which contain free acids, they are partially soluble in hot water, because we know that acids are normally soluble in water, and they are largely used for their essence, for their fragrance, as we will discuss in their traditional uses, they are largely used for their essence or the fragrance or their perfume, and they are also used for their antiseptic as well as stimulant properties. And you can see the example in the picture, balsam of Tolu. A person is on the tree of balsam tree, and he is inflicting injury onto that particular tree and thereby collecting that particular balsamic resin. Other examples of resins are balsam of Peru and Canada balsam. Now, Canada balsam is obtained from Abies balsamea, and I'm sure everybody knows about Canada balsam, that this is a type of balsamic resin which is largely used in microscopic study and to fix the section or to prepare the permanent slides. Now, why it is used in preparing permanent slide? Because the resin, it is mainly composed of the non-volatile diterpenoids and small amount of the volatile constituents. So, whenever that resin or the balsam is collected from Abies balsamea, it is basically heated to evaporate the volatile constituent, and those non-volatile constituents, they form a very fine and shiny film, and that film is having refractive index similar to that of the glass, and this is the reason why Canada balsam is largely used in microscopic studies. Obviously now numerous synthetic resins are available in the market, but still some people still prefer this natural Canada balsam for the microscopic studies. So friends, now we move on to the last portion of our lecture, that is the uses of these resins. Now, for plants, as we discussed, these resins act as defensive chemicals. So whenever an injury is inflicted onto the plant immediately start producing these resin substances, or it starts secreting resin substances as a part of its defensive mechanism. So largely they protect the plant from any kind of bacterial infection or any kind of fungal infection, or if any injury is given to the plant, they start secreting the resin, and that resin basically covers the injured portion or the area of that plant in order to allow the internal machinery of the plant to recover and start dividing to form the new cells in that particular area. So this is how basically they act as defensive chemicals. Traditionally, these were largely used for their essence or their perfume. They were also used in making jewelry. As you can see in the slide, this jewelry is made up of a resin, and for essence purpose, myrrh was largely used. Even today you will find myrrh essence sticks available in the market. Since these resins are water insoluble, these were also used to protect the oil paintings or the traditional art pieces from various environmental oxidation and to protect them from any environmental moisture or water. They were also used in manufacturing of varnishes to protect the wooden furniture. So these were few traditional uses of resins. So now we move on to the industrial uses or the commercial uses of resins. Now, resins are widely used in the preparation of plasters because of their adhesive nature or sticky nature. They are also used in various kind of ointments which are meant for antiseptic purpose or localized. If you want to provide localized stimulation in a particular area, then such ointments containing resins are also used. Resin tree or the resins that are obtained from the species of Copaiferra are largely used in the manufacturing of biodiesel, and that is why the tree which is known as Copaiferra langsdorffi, it is also known as the diesel tree. Now, the resin of this tree, it is rich in sesquiterpene hydrocarbons and has shown properties similar to that of the fossil fuel, that is the diesel, and therefore it is known as a biodiesel, and lot of work is being done on this plant and on the fuel that is obtained from the resin to basically I will say replace the fossil fuel, which is the normal diesel which we are using nowadays. Next, the resin trees, they play an important role in agroforestry because a lot of cultivation of these resin trees is being done, And since the resins have I will say a lot of commercial usage, therefore large areas are there which are under cultivation of resin producing trees, and therefore I said that resins also help in the development of agroforestry. Vis-a-vis, they also help in the ecological development of that particular area. They also provide ecological diversity in that particular area. So this is how basically they are helpful and they're commercially they are useful. And last but not the least, they are used widely in the manufacturing of paints and varnishes, and the resin specifically obtained from Pistachia lentiscus, it is largely used in the manufacturing of the varnishes that is being applied on the wooden furniture or the wooden boards in order to protect it from bacterial infection, termite infection, or any kind of harmful effect caused by the moisture. Now we move on to the medicinal uses of resins. Like the resins have wide variety of commercial usage, they also have wide medicinal or therapeutic uses. Beginning from anti-cancer properties, the example is podophyllum resin or the podophyllum. We all know that this plant is well known for its anti-cancer properties and is a well-established anti-cancer drug. And resins, most of the resins have also shown antimicrobial properties. So because as we discussed that the plant produce these resins as their defensive chemicals against various bacterial or fungal infections, so these resins have very good antimicrobial or antibacterial or antifungal activity. Then resin of guggul, which is normally obtained from Commiphora vitae and commonly we known as guglu or guggul, it has shown significant cholesterol lowering properties, that is hypolipidemic, and a lot of work has been done on guggul for its hypolipidemic activity, and significant positive results have been obtained for its hypolipidemic activity. And since guggul is widely used commercially also, there has lot of exploitation of the guggul tree, and now Government of India has completely banned the wild tapping of the guggul trees to collect the resin, and guggul has been declared as an endangered species. Now you can only collect the guggul by tapping the cultivated trees only, and Mangliewa's Guggul Bachao Abhiyan is well known in our country in order to protect this precious resin producing plant. Likewise, guggul also exhibited potent anti-inflammatory activity for the joint pain or any kind of inflammation in the body. Guggul has shown tremendous results against inflammation, and since guggul has been declared endangered plant, so its substitute has been developed, which is known as Salai guggul, and this Salai guggul is the resin that is obtained from Boswellia serrata, and the Salai guggul has shown almost similar kind of biological activity or therapeutic activity as that of the guggul. Then certain resin producing plants are also used in management of pain, and the most common example is cannabis or bhang. Then it is also widely used in various CNS disorders like anxiety, convulsions, or if you insomnia. If you want to depress the hyperactive CNS, you can also use cannabis. Even cannabinoids, which are the major components of cannabis, they have shown protective action against various memory disorders also. Certain types of resins like asafoetida and ginger resin, they are widely used in overcoming various GI disorders. They cause increased secretions in gastrointestinal tract, thereby increasing your digestion, as well as they are good carminative, thereby reducing the flatulence. And as we discussed, resins have very good antiseptic and wound healing properties, specifically the balsamic resins. And some of the resins have exhibited expectorant and stimulant action as well, and the most common examples are colophony and ginger. So friends, this was all about resins, right from their definition to their distribution to their properties to the organs from where they are secreted, from the site where they are synthesized, how those storage sites are created inside the plant, what is their properties, what are their compositions of the resin, how they are classified, and finally we discuss about the uses of these commercially important secondary metabolites. Thank you.